Hi, everybody. This is Nalini Elkins with Industry Network Technology Council, and today we're going to talk about a role and do some trace reading. Thanks. I'm hearing that the sound is okay. That's perfect. Thank you so much. You guys know the drill. If you ever have problems or anything, just send me a quick message. As always, this session is being recorded, just so that that you know. So this session is part of a multi-year effort to help enterprises with IPv6 deployment, and we're going to help training, which we have been doing, and this is a part of that webinar. We're looking at doing a new set of webinars starting in the fall, adding, of course, onto the IPv6 work that we've been doing, but we'll also probably head more over into the security area. And so if you guys have ideas, anything like that, topics you'd like covered, now would be a perfect opportunity to get your wishes in, because we're in the process of deciding what we're going to, the series of webinars that we'll offer coming in the fall. So these webinars are made possible by a grant from ISIF Asia. Thank you so much. We have received grants from Aaron and ISIF Asia for a number of years, and we're very happy for the relationship. So I'm going to quickly go past mine, and so that we can talk about what's really interesting, which is Rahul and the work that he's doing and the things that he's going to show us. Rahul has a great deal of expertise in implementing these protocols, and in particular having them go into commercial products, because that's a whole different stage of evolution. It completes the cycle from getting the idea, seeing it standardized at the IETF, then actually getting the hands-on implementation. That last part is incredibly good feedback to feed right back into the standards and to know how standards really operate. And for me, in a lot of ways, that's the most exciting part. It's all well and good to have an idea, but how does it really work? And that is what Rahul is going to tell us today. And he's going to use a lot of packet tracing, which is actually, as far as I'm concerned, the best way to learn. You know, packets don't lie, and when I start seeing packet tracing, then that's when I really start understanding. And I hope you will feel the same way. So I'm going to go ahead and turn that over to Rahul, let him show his screen, and thank you so much, Rahul, for presenting.
Thank you, Nalini.
Rahul,
can you hear me?
Yes, we can hear you, but we can't see your screen.
Oh, you can't see my screen? Oh.
Well, I tried to
Click to start. Okay, can you send the invite again for the screen sharing?
Yeah. So I'm going to show my screen, and then I'm going to send the invite to you again. You should have a pop-up.
I did get a pop-up, and I clicked on show my screen. So it should start sharing, right? Do you see my screen?
No, we don't. Is your web on for anything?
Is my what, sorry, on? The web camera?
Your web. Yeah.
Nope. No.
Okay, so you know what I'm going to do? Why don't you try for a minute, and then I will go ahead and I can show your screens from my laptop also. So let me get ready for that, and then give you one more minute to see if you can show it. There you, perfect. Perfect.
It takes some
Yeah,
time.
there.
It works. All right. Okay.
Okay, okay. Mm-hmm.
So hello everyone. I'm Rahul Jadhav. Pleased to see you all here. I'm going to talk about RPL, the mesh routing protocol typically used in low power and lossy networks. RPL stands for Routing Protocol for LLNs. LLN stands for Low Power and Lossy Networks. It's basically IoT networks which are highly constrained. Like when I say highly constrained, uh, typically 802.15.4 or PLC networks, those are the networks that have been considered for such protocol deployments. So I'm going to, so this is the agenda. Let me just start the slideshow.
Yeah, perfect. Yeah, I was just going to say it'd be great if we can see it full screen. Thank you.
Awesome. All right, so this is the agenda. I know that there had been few RPL sessions handled already from Pascal to, but no, so you've heard it from the guru already, but I would still provide a quick refresher as to some of the important concepts of RPL, what differentiates RPL from other routing protocols and why it makes sense to be used in low power and lossy networks. Then I'll get into what we are here for, RPL signaling and packet trace reading. Then I have an interesting bit where I'll simulate a sample network. I'll show you the network formation. I'm going to use a tool called as Whitefield for that purpose, and then going to talk about what are the best practices for doing performance evaluations with large scale IoT networks. A lot of papers out there get it wrong. A lot of folks, I personally suffered from problems when dealing with scale. Some of those experiences I'm going to quote in here. Hope it makes sense. So just a quick background, why 6LoWPAN or RPL, or before why 6LoWPAN or RPL, why mesh in the first place, right? I mean, hub and spoke model has been used for decades. It works great. What's the problem? Typically, the problem is scale, right? The range that you want to achieve. And you can't go ahead and put in extenders in all the places. It's going to degrade the communication extensively. Not only that is one of the problem, but bigger problem than that is in case of IoT networks, there could be a lot of P2P traffic. What happens in a hub and spoke model is that typically there is a densification of traffic at the router through which everyone connects. So you'll see a very hot spot there that eventually becomes the bottleneck. And if that router goes down, then you need a backup router, and it's a mess to get it working. With mesh, you can have devices interconnecting with each other. Even if one device goes down, there is a self-healing property of these networks where they'll automatically find out another best available path and figure out how to send the traffic. That is why everyone will use mesh. That has been the primary reason why we adopted mesh in my previous organization. Basically, the use case that we were targeting was smart grid networks, where we had very constrained devices on the meters, and there were two types of networks used there. One was 802.15.4 network, and the other was PLC networks, and we had to operate hundreds of devices in this scenario. Now, coming to 6LoWPAN and RPL, now we've been talking about constraints. The network that we are talking about here has a constraint, usually 802.15.4 standard. 802.15.4 has a constraint of 127 bytes MTU, which is extremely low. So you need header compression to work. There had been header compression algorithms used before 6LoWPAN came into picture, but those were mostly stateful compression techniques like ROHC, robust header compression mechanism. They require state to be maintained. In case of IoT devices, maintaining that state is extremely costly. It requires resources. It requires you to synchronize the state over a period of time. In the case of lossy networks, it becomes more painful to operate. 6LoWPAN basically provides you mostly headerless, stateless header compression on interfaces with low MTUs, such as 802.15.4 and power line communication for that matter. RPL is a mesh network protocol, mesh routing protocol. So you have 6LoWPAN at a lower level at an where the IP header compression and transport header compression are handled by 6LoWPAN header compression, and RPL is operates on top of ICMP. It's a routing protocol. The primary operational principle for RPL is underreact to failures. Because of these lossy networks, because of these constraints, if you overreact or even react moderately to failures, it is going to cause more. It's going to increase the loss rate in the overall network than fix it. So if you see a failure, if a node sees a failure, it's not going to send hello message and try to check if the previous node is available. So that kind of operations are typically avoided by RPL. Hello messaging altogether is avoided by RPL, and in subsequent slides I'll take you through what exactly is done. Then RPL is primarily optimized for multi-part to part and multi-peer to peer and peer to multi-peer traffic. Essentially, all the sensors sending data to the cloud. That's multi-part MP2P traffic, and the other way around is P2MP traffic. That is what it is optimized for. P2P traffic is not so optimized. The default RFC 6550 of RPL is not so optimized for P2P traffic. There are reasons quoted in other observational drafts in IETF about why is it not optimized. DAO projection work. I think the previous presentation in this series talked about DAO projection and how it optimizes the P2P traffic for these conditions. So 6LoWPAN and RPL, the primary reason 6LoWPAN is used because of the constraints, the bandwidth constraints, the MTU constraints. You cannot afford to send a 40-byte IPv6 header. So you have to compress it. You cannot afford to send a 20-byte or 8-byte UDP header. So how do you compress it? That's what 6LoWPAN deals with. And RPL is basically a mesh routing protocol for these. So there are these three types of node types in RPL. One is the root. The other, there are router nodes. So nodes which advertise themselves as router nodes. And then there could be leaf nodes which do not necessarily take part in routing others' traffic, but they still join the network. They can still join the network as leaf nodes. I'm going to skim through these some of these points very fast because my assumption is that previously there had been sessions on this topic, which might have taken you through some details. But this is a refresher wherein I still need to talk about, because I'll be using some of these terms in packet trace reading in the subsequent slides and wireshark reading. There are two modes of operation supported by RPL. One is, and the most popular one is the non-storing mode, where intermediate 6LRs, the router nodes, do not have to maintain any routing tables. So this is the sample of non-storing mode MOP, where there is no routing. Routing table is maintained only on the root. So root maintains how to reach all the nodes within the network who have advertised themselves to be reachable. And when the packet has to be sent, source routing is being made use of to send the packets to individual nodes. So that's how non-storing mode works. With this mechanism, because of source routing header being made use of, the packet internally carries the state as to which should be the next hop that should be sent to. In case of storing mode, the routing tables are maintained on 6LRs, which means that root does not have to. Root still has to maintain the whole routing table, but when the packets are sent, the data plane packets, they do not have to carry source routing header, which means the control overhead for data plane packets is much less. But then the resource requirement on the 6LRs is slightly more. Rank, every node in an RPL network has a rank. I think this is not uncommon for any routing protocol. So in a hierarchical structure, every node has a rank, and for every level there is the same nodes on the same level have equal or approximately equal ranks. I have to talk about few more things before I jump into the packet reading. There is something called as RPL DODAGs. So RPL essentially forms a network in the form of a directed acyclic graph, which means there ideally won't be any loops. If there are loops, those loops will be resolved. There could be multiple DODAGs within an instance. So I'll talk about instance in a little while, but there is a notion of DODAGs in RPL, wherein a particular node could be part of only a single DODAG within the same instance. Typically, the use case here is if you want to load balance the network. So let's say, for example, there are two border routers, and these two border routers announce the same, use the same RPL instance, but they want to distribute the traffic, distribute the nodes among us themselves. So this is how typically how typically the DODAGs will be operated. So this border router will use the same instance ID 0. Objective function is 0. Objective function is essentially the metric function. How do you calculate a rank, and how do you make use of the metrics to finally decide which rank the particular node will belong to? So instance ID is 0 for both the border routers. DODAG ID 1. DODAG ID is essentially the IPv6 address of the root. Typically, it is the IPv6 address of the root. So you have border router 1, border router 2, each of them announcing its own DODAG ID, but as part of the same RPL instance ID, which is 0. They then split the node equally amongst themselves. That's one of the important aspect of RPL DODAGs. Now, what is the significance of RPL instance? Let's say you want to form multiple paths or multiple trees with different characteristics. So if you see in these two diagrams, left and right, you have the same nodes, but the network formation is different. We have green nodes, which are battery powered, and yellow nodes, which are active energy powered. And ideally, in this case where data traffic is being sent by all the nodes, green nodes only act as leaf nodes. So in this instance, green node announce themselves as leaf nodes, but then there is another instance where this instance could be used to send alerts, important alerts or critical alerts, where even green nodes can announce themselves as being okay to be used as 6LRs or routers. So you can have this kind of formation. This is the typical use case for multi-instances and multi-DODAGs. This has been one of the sources of confusion in the community about what is the difference between instances versus DODAGs. Now, let's come to RPL signaling. Now I'm talking brass tacks. What are the signaling messages that are used? Typically, there are three primary messages. There are more, but there are three primary messages. One is the DIO, or even before DIO, let's talk about DODAG information solicitation, DIS message. Then there is DIO and DAO message. DIO and DIS are typically multicast, not necessarily multicast, but in 90% of cases, these will be multicast packets. DAO is mostly a unicast packet. It basically is used. So there are two streams. This is the downstream going from sink to the to the higher ranks. That is the downstream traffic, and the upstream traffic is the node sending the packet towards the sink. That's the upstream traffic. So DAO usually traverses upstream. DIO, which is the multicast message, is usually flows downstream. The aim of DIO is to establish the connectivity upstream. So this can be really confusing. So when this sink sends a DIO message, node 1 and 2 gets that message because it's a multicast message and they are directly available. Even if there are specific edges shown here, these are wireless links. So showing an edges is just for representation purpose. So sink sends a DIO, which is received by node 1 and 2. Node 1 and 2 in turn might send DIOs because they are 6LRs. They are routers, so they will in turn forward the DIOs based on the configuration that was sent by sink. And then if node 1 and node 2 or other nodes want to be addressed directly from sink or from the external network anywhere outside of sink or root, I don't know why I'm using that term. Sink is equivalent to root. Root is the most widely used term in case of RPL. So if the nodes intend to be addressed from the from the root or from the node or from the external network, they would typically send a DAO saying that I am located here. This is my immediate preferred parent, and if you want me to send the packets, this is my route. So DAO is the unicast packet that is usually sent to root directly in non-storing mode, and in case of storing mode, it is sent to the preferred parent. Anyways, again, I'll go into the details of how exactly the signaling works. For the sake of this discussion, the important thing to note is that there are three primary messages. I'm also going to introduce a traces or PCAP for 6LoWPAN messages. Again, 6LoWPAN message, 6LoWPAN is for header compression. You can do transport header compression as well. And based on the actual packet capture, I'll show you how it is done. For the most part, there is the 6LoWPAN compression does not require state to be maintained. Now, okay, so before going into the details, before showing that packet trace, let me see if I have the packet trace up. I have the packet traces up. A typical RPL message is split into two parts. One is the base message. The base message is what I called up for as DIO, DAO, and DIS. So these are the base messages. And then there could be one or more options, or even zero options, zero or more options, followed by the base message. Those options are typically called control options. In case of this is a message which is sent by 6LR nodes to solicit DIOs from immediate peers. So what happens is when the network starts up, a particular 6LR is waiting for a network to join. If the node doesn't get a DIO from the upstream parent, then the node will send a multicast disk saying that I'm waiting. Please send me some connectivity information. That's essentially DODAG information solicitation. This is typically never sent by the root. It can be sent by the root, but the multicast disk is never sent by a root. It is used by 6LNs and 6LRs to query, to check whether there are any parents or whether there are any nodes in the network, and basically it solicits DIO. DIO contains the information of the nodes, networks that typically the node want to join. There is only one supported control option. Like I mentioned in the previous slide, there could be there is a base message. In case of this is the base message. And then you could have a solicited information option, which is this. I've not seen any, not many of the implementations makes use of this particular information option. But basically there exists an option where you can individually query for a given RPL instance ID. The node would like to understand what the corresponding parameters are. So in response to a unicast, a node can set a unicast disk to a particular node, to a particular peer, and get a unicast DIO in response. So this is the most simplest of the message. Here you can see I have a network which essentially consists of like 10 nodes. You see here node number B 2 0 1, sorry, and 0 is not sending this. 0 is the root node in my case. All the nodes from 1 and above are 6LRs in this network, and when the network starts up, they send this packet to probe if there are any instances operating in the network, RPL instances operating. It's a very simple. So let me first quickly skim through the 6LoWPAN headers. Usually there is an IPHC header where it specifies whether the traffic class and flow label are compressed. Usually the predefined traffic class and predefined flow label is being made use of. The hop limit, there are 2 bits for hop limit. So 0x2 stands for 64 hop limit. Context identifier extension. There is something called as you can have certain prefixes, IPv6 prefixes and context identifier for any of those prefixes. For example, AAA colon colon could be one prefix, BBBB colon colon could be another prefix associated with context ID 1 or 2. So basically, those can be used to create the source or destination address. Here, what is the context identifier is extension is false, which means it's not used. The source address compression mentioned here is stateless. Source address mode is mentioned as compressed. So what it means is that the source context is FE80. It's a link local prefix. The source address is going to be compressed, which means that you derive the source IP address of this source IP address based on FE80 colon colon and the MAC address of that particular node. So if you see here, the MAC address is source is 0001. So based on this combined together gives you the address, this FE80 colon colon 1. So this is what is derived from this. Since this is a multicast packet, there is a multicast address compression is also set to true. And yeah, it is the same point. In case of RPL, this is a well-known multicast address. FF02 colon 1A is a well-known multicast address which is reserved for RPL message multicasting. So that's about it, about 6-LoWPAN header. You can see in the wireshark that, why is this not visible? So the whole frame is the compressed frame. I'm going to just okay. Yeah, for some reason this is getting cut out. But if you see, the compressed frame is 23 bytes and the decompressed 6-LoWPAN IPSC is 46 bytes. That's the kind of compression you get, 46 byte, yeah, 46 bytes. Yeah, you can see in the tooltip. And the compressed header is 23 bytes. So you get almost 50% reduction, and in a lot of cases even better than that. So that's about 6-LoWPAN. This header is reconstructed header. Wireshark automatically reconstruct the header based on 6-LoWPAN and the MAC header, and shows the full IPv6 header here. This is full 40 bytes header, but on the wire, this on the wireless link, this doesn't get sent. Then there is ICMP header. So here there is a predefined type for RPL control messages. 155 is the number. Then within any ICMP type, there could be further codes for every type. It's a standard ICMP format. For RPL control messages 155, there could be further codes like 0 is for dis, 1 is for DIO, 2 is for DAO, and things like that. Forget about the checksum being incorrect here. It's just a warning. And then there are flags and reserved bits here. So if you see here, the flags and the reserved bits, options, there are no options in this. So essentially the whole, there we go. This is what I was doing now. So if you see, the whole ICMP message is in 6 bytes, 1 byte, 2 byte. The flags are 1 byte, and the reserved flags and reserved are 2 bytes, right? So that's an easy one. DODAG information solicitation. So if you see, this is a multicast packet sent by non-root nodes to solicit DIOs from other nodes who are already part of the existing network. So what happens is, in this network, let's say for example, root has started and these nodes start up first. None of the other nodes are already joined to the network, let's say for example. So these two nodes, 1 and 2, will send DIS message saying that we are checking if there is any RPL network to which we can join, and the root will then send a DIO saying that here you are, check if this works for you. So that's about DIS. Now DIO is one of the most important message. Again, it trickles downstream from root to the ranks with higher ranks towards the higher ranks. DIO again is a multicast message. It is emitted only by 6LRs and the root node. I forgot to mention here the root node. So root node and 6LRs will emit this message. 6LRs will emit this message only if they have already joined the network, which means that they are ready to take other nodes. So they are ready to operate as a parent node. That is what it typically means. They are ready to operate as a RPL parent node. Now, important fields, again, this is the base object. There are a lot of important fields in the base object itself. The first being RPL instance ID. Like I've mentioned previously, every RPL network consists of an RPL instance and DODAG. There could be multiple DODAGs within the same instance. A typical node could be part of multiple instances within the same network, but they could be part of only a single DODAG. There is a rank field. Again, the rank is calculated by the node. It is usually based on, so there is a relation between a metric and a rank. If you have, the metrics usually checks how good your immediate connectivity to the parent is. The rank is where that node exists within the overall network. Usually there is something called as rank offset. Typically the rank is increased not atomically, monotonically. It's increased by a certain factor. By default, it is, I believe, it could be anything. It could be 16. In case of Contic implementation, I think they make use of 16, or it could be as high as 128 or 256 as well. Then mode of operation. I mentioned mode of operation before, which is either storing mode of operation or non-storing mode of operation. The root node decides what should be the mode of operation, and all the other nodes simply follow that. There is also a G bit here. The G bit stands for grounded DODAG, which means that through this DODAG, one would be able to reach the root and the outside network. It is possible that any node within the RPL network can start a local floating DODAG. It's called a floating DODAG. If some node wants to establish a path towards itself from all the other nodes, they can initiate something called as a floating DODAG. Grounded DODAG is typically initiated by a root node which has external connectivity as well. There is a preference. So what is the preference of this RPL instance ID in the overall, if there are multiple instances used? DTSN, this is a sequence number, destination transit sequence number. I'm not sure what T stands for. I think, okay, let's check in the PCAP. So the important task of this DTSN is it triggers the DAO message from the downstream node, from the child nodes. If the DTSN is increased, it tells the child node that you have to trigger the DAO message. Basically, it can be used to refresh the whole RPL network. Typically, it is used by root to refresh the whole RPL network. Then there are certain flags and reserved bits. DODAG ID, again, like I mentioned, you can have multiple DODAGs within the same instance ID. DODAG usually is the IPv6 address of the node which is initiating this instance. In case of root node, this will be the root IPv6 address of the root node. Then the DIO message can have one or more options. Usually there are one or more options. DODAG configuration is one such option. Most of the implementation today by default send this DODAG configuration option. It basically gives you the parameters. So the network requires, what is the frequency at which the DIO should be sent. There is something called as a trickle algorithm that RPL makes use of, which exponentially increases its time factor for sending the DIOs. what would be the what are the parameters that are controlling the trickle algorithm is decided by this DIO redundancy, DIO integer doubling, and redundancy factors. There is something called as OCP as well. OCP is objective code point. It tells you what is the objective function for metric calculation that is used. Again, all these parameters are set by root node. All the other nodes in the network will simply propagate this further downstream. The nodes usually are not allowed to change this. Usually, it's not allowed to change this any of these configuration parameters. Okay, and then there is prefix information option. I forgot to add the format here, but let's go into the trace reading. Now DIO is an important message. You can see it's a little bit bigger packet. Now 6-LoWPAN headers are common. You can see RPL control type is 155. The code type is 1. RPL instance ID is 30 in this case. It stands for this is a the instance ID is 30. The version is 240. There is again a notion of something called as lollipop counters. I think I have a representation of lollipop counters. So lollipop counters are typically used to rotate through the versions or any counters. Most of the counters that are used by RPL are a single byte counters, 1 byte counters, which means that it does not have so much of entropy. So lollipop counter mechanism it provides you with how do you identify if it's an old message versus a new message. So I would suggest folks to look into lollipop counters. It's one of the technical points about how to maintain counters in low MTU networks. Rank, like I mentioned, so 0 starts with a rank of 128. So this is the minimum rank in this network. Then there are flags. You can see grounded flag is false. Mode of operation is storing mode of operation with no multicast support. That's mode number 2. DODAG preference is set to 0 because there is a single DODAG operating. Destination advertisement trigger sequence number, DTSN. So when I said that when the root node typically will use, or the parent node 6LR in case of storing mode of operation, will typically increase this DTSN to refresh the routes of the downstream nodes. If this is incremented, downstream nodes sees that okay, the nodes above me require me to refresh the routes, so I need to send the DAO message again. So this is to trigger the DAO message. DODAG ID, like I mentioned, DODAG ID is the it's usually the global or GUA based IPv6 address of the root, and then there is DODAG configuration option. Like I mentioned, these are all the parameters used for trickle algorithms: DIO interval doublings, DIO interval mean, DIO redundancy constant. All these are objective code point is the objective function value that should be used. Lifetime and default lifetime. So typically lifetime is a 4-byte integer in other routing protocols, but since there is limited MTU in case of the networks that we're talking about, the lifetime, there is a lifetime unit, so it's a multiple of this lifetime unit. So every lifetime that is mentioned in the packet is a multiple of this unit, 60 seconds. We have prefix information options. So one of the intention of the root is to initiate a network creation, and that network creation requires all the nodes in the network to have a prefix, IPv6 prefix. So this is the prefix that is advertised by the root. All the nodes should join the network using this prefix. So that's DIO. Now, like I mentioned, DIO is a multicast message. It trickles downstream. Now, the last most important message is the DAO, the destination advertisement object. This is typically a unicast message emitted by 6LNs, the leaf nodes, or 6LRs. Any node who would like to be addressed within the network, directly addressed within the network, would use it. Not all the nodes have this requirement, by the way. It is possible that the node might never send a DAO, in which case it means that it is never addressed. So for example, a typical use case is if a node wants to just send out messages upstream and never wants to get addressed directly from the root node, then in that case, the DAO message will never be sent. So this is the base message for DAO. The DODAG ID is an optional field. Typically, it is not used. RPL instance is the same RPL instance ID which is advertised in DIO message. DAO sequence is another sequence counter. So how fresh, the freshness of the DAO message is defined by the DAO sequence counter. Again, this is a lollipop counter. All the counters within RPL are lollipop counters. It's a special algorithm used for counter operations for low power and lossy networks. Now, what are the control options used in the context of DAO? There is, the DAO is typically sent by a node to send its own target address. So DAO will be sent by the node saying that this is my address. You can send packets to me on this particular IP address. So that's the prefix. That's the full target address that is mentioned. In case of non-storing mode, the parent address is also sent. So the root node has to create the whole source routing header. In case of non-storing mode, the parent address is part of this packet as well. Let me quickly jump into the RPL control destination advertisement object. Now you can see the same type. Code 2 is the destination advertisement object. RPL instance ID is the same RPL instance ID which was advertised in DIO. DODAG ID present. So is the DODAG ID present? True, which means that the DODAG ID is part of the DAO message. And acknowledgement does it require a DAO-ACK to be sent? Since DAO is a unicast message, it could additionally have an acknowledgement. In this case, it is set to false. We don't need a DAO-ACK. The target message. So this node number 14 is advertising that this is my target IP address, IPv6 address. Root or any other intermediate node can reach me using this particular IP address. That's the information that is. Transit information option. These are additional options like path sequence, how fresh the path is, what is the lifetime of the path. All these information is sent as part of transit information. Now, multiple targets might be preceded by a single transit options, which means that all those targets will use a single transit information. Yeah, typically every target, one or more target will be preceded by a transit information option. You can see a packet 802.15.4 packet, which is an ACK packet. This is not a DAO-ACK packet. This is an ACK which is initiated at the link layer. So you see there is no IP header here. You can configure 802.15.4 interface wherein all the unicast packets will be sent with an ACK. It's a link layer ACK. So that's the link layer ACK that is shown. It's not part of RPL messages. Only the pink color messages are part of RPL. Those are the primary messages from RPL, and then there is DAO-ACK. Like I had mentioned, it's a unicast ACK to DAO, used typically to ensure that end-to-end connectivity is established. For example, when a node sends a DAO-ACK to the root, how would the node know that the DAO has reached all the way to the root? So root will respond. So one way for the node to know is it can send an ACK. It can set the ACK bit. When it receives the ACK flag, it knows that the end-to-end connectivity within the mesh network has been established. No-Path DAO to handle the route cleanup. The only difference between DAO and No-Path DAO is that the path lifetime is set to 0, indicating cleanup. Okay, I'm going to simulate a sample network. Nandini, quick time check. How much time do we have left?
We have 15 minutes left.
Okay.
I will go over a little bit if you want to. Yeah.
Okay. All right. So I just want to show a sample network, create a sample network. And so I'm using a software simulation framework here called as Whitefield. What it does is it does a realistic simulation of multiple nodes. You can have 100 nodes. If you want to simulate 100 node network and with realistic conditions, how are the realistic conditions simulated? Using NS3 or Castalia, like simulation backends. So you can have PLC based simulation or 802.15.4 based simulation, and you can have any operating system here. So today we support, today the Whitefield support Contiki and Riot. Again, all this is out there in open source. The GitHub link is mentioned here. I'm going to quickly show, since the Whitefield is not started here, this won't work. Let me start the network first. So, okay. There is this configuration file that Whitefield uses. Number of nodes at 10. How is the number of nodes? How are these 10 nodes distributed within the network? There is a area of 400 cross 400 meters. The topology is a grid topology, and the grid width is 5. The PAN ID, it's a link layer ID. It's ABCD. What are the nodes stack lines, which means that what are the operating systems that are operating on the node? In this example, I'm making use of Contiki. There is a Contiki UDP client example and UDP server example. On the node 0, I'm running a UDP server. So basically, this is the configuration that I'll use. This is a 10 node network. I'll start the network, basically provide this. Yeah, I've started the network. I'll start listening on this. And then Okay, so we see that the 10 node network is being formed here. What I'll do is, for the sake of this discussion, I'm going to stop this network and then update the configuration to put 20 nodes in the same network. Okay, this is just so that you get an idea of what's happening here. So I've started the network again. Yeah, so it's a 20 node network now, and you can see how the network is getting formed. So essentially, the DIO messages is sent, and then the upstream parent connectivity is established. In some cases, you can see that the nodes are switching the parent connectivity. So this is the actual node. So here, the root node here is node number 0. After some time, the network will stabilize, and this is the position-based view. It's a grid network. If you want a tree-based view, you can get the tree-based view as well. Again, it's a very minimal. Most of the commands that are used on the CLI aspect. We just have a sample pictorial representation of how the network is forming and changing. So yeah, now the network has in a way stabilized. Initially, for the few minutes, the network usually oscillates and then stabilizes, and then there is much less RPL messages floating in the network. Okay. So what is the use case that I want to show is, if you are dealing with a IoT scenario which requires like more than 10, 50 or 100 nodes to be simulated, there are no other tools. Either you have two options. Either you can directly use NS3, but if you directly use NS3, you can't directly use Contiki, Riot, or any other standard operating systems, embedded operating systems like FreeRTOS directly on NS3. You can use Whitefield to actually simulate these kind of networks. The last point that I would like to make is about capturing the performance data the right way. Typically what I've seen is people making use of Kuja. That is one of the foremost tool that has been made use of to capture performance data. While Kuja does not do realistic wireless simulation, which means that the data that is captured in most cases is not close to the real world scenario. Me and my team in Huawei faced major issues with this behavior of these simulation tools. And when we tried the 300 node network, it worked great in Kuja, but then when we actually deployed it in real environment, we saw that it didn't scale. The RPL didn't scale to the needs that we had, and that's when we went back to IETF proposing some of the changes to the RPL protocol. There are two case studies that are mentioned here. Again, I won't go into the details. The first is the performance evaluation of efficient route invalidation. It's an RFC today, 9009. Basically, how do you improve route cleanups in an RPL network? This was simulated in as part of Whitefield. And then there is a performance evaluation of 6-low fragment forwarding. It's again a nice piece of work from Pascal. So we had done a performance evaluation of that. So again, all these performance evaluations are available online. I'd be happy to share the slides. I guess that's it. Nalini, do we have any questions? Do we have any next steps?
Yes. So sure. No, thank you so much, Rahul. It's very, very interesting. If guys, if you have questions, please go ahead and ask, or if you want to talk, raise your hand and I can unmute you. And meanwhile, I'll go ahead and start with some of the questions that I myself have from listening to this. So, okay, so maybe I'm misunderstanding, or it's like there's a lot to catch up on, and then absorb from what Pascal said too. But am I correct that these messages are being sent out to and from the root and so forth in two ways? One, there's no it seems like there's no encryption, and two, no authentication. Am I correct in that, or have I missed something along the way here?
No, RPL does have a section which says how do you do encryption of RPL control messages. You'll have to use a appreciate key. So there is a section detailing out how do you handle the encryption, how do you do secure RPL signaling. Having said that, none of the instances, none of the implementations I know of depend upon that security feature. Most of the implementation use the security feature that is already provided by link layer. So there is already a link, all the link layer messages, they secure all the above messages, So that's the security most of the implementations are making use of today. I don't know of any implementation which is making use of the secure mode for RPL signaling today. Most of them are reliant on the data link layer security features. But yes, RPL. Sorry.
No, please continue. I thought you were finished.
The only thing I wanted to say is that yes, there is an explicit section in RPL dedicated to handling secure RPL signaling, which gives you an idea about how do you secure packets for RPL. How the key should be used, all the best practices that should be followed for secure messaging. Yeah.
But I see. So you would use pre-shared key. But what can you go into a little bit more about what you mean by link layer security?
Yeah. So when I say link layer security, what I mean is 802.15.4 itself has a security layer. In this wireshark, it is not used, but by default, in any practical implementation, in any implementation, there is a security field. There is a security handling done at the link layer, which means that all the messages above it are secure. So currently the security enabled is false here, but in practical deployment scenarios, this security flag is set to true, and the packet is encrypted based on the link layer using the link layer's security. So the payload for the payload, the whole of payload from above the link layer headers is secured using the same primitives which link layers.
That's very, very interesting because, I was just thinking to myself, it'd be very easy for me to, depending on if I had access to the people's environment, if I walk into a hospital or something, and then if they're, as I say, I'm not giving anybody any ideas, but if I walk into a hospital and, Raspberry Pi or something, like, can I make myself root? You know what I'm saying?
No, but then how would you get the key which is used for the link layer header? So unless and until someone adds you to that network, to that, like in case of Wi-Fi, unless and until you are part of that network, you won't really be able to send messages or view messages. But let's say if someone adds you, again, I know there are issues with this kind of security mode, so there are ifs and buts here. But if someone ends up adding your device as part of that wireless network, then yes, your device can wreak havoc. It can announce itself as a root. It can announce it will start sending DIO messages with ranks. It can redirect all the traffic to itself. Yes, it can cause a lot of issues if you get such kind of device introduced in the network. Yes.
Sorry, I shouldn't be laughing. It's not funny. But no, this is a super interesting area. I mean, as I say, I think I might have said before, is I just installed a smart lock on my door, and I wanted to see if I can hack into my own house. I think it's super, super interesting. I think that one of the things I'm thinking too, in practical implementations, what do we tell enterprises that they shouldn't do? Probably one of the things is like, don't be letting people onto that Wi-Fi network.
No. Yeah. And so let me say, the use case that you're describing is a very different use case. So usually RPL has found its entry into not into home automation solutions. It is more widely used in smart grid networks and other industrial networks, where the one who is managing the network is inducing all the network nodes. So it's centrally controlled by an enterprise as to which nodes gets added as part of that network. So that's where it makes sense. In case of home automation scenarios where you will just casually add any node, in that case there will be problems. I would suggest have a look at Google Open Thread. That operates primarily from home automation and building automation perspective, but it does not make use of RPL as a mesh routing protocol. It has its own variation of routing protocol used for certain reasons. It's a derivative of RIP v2 protocol, is what I understand. But for home automation and building automation, there's a different mesh protocol being used.
Great. This is very, very interesting. If anybody else has any questions, please feel free. Otherwise, thank you so much. What I'd love to do is if we can have the packet traces, and also we can start a link. I'll talk to Dhruv and the other folks at IISOC, and for INTC also, is what I'd love to do is start some information pages with both the traces that you have and also the link to the Whitefield, was it? And that demonstration tool. I think that sounds certainly to get to know what's going on. I think that would be very, very interesting to go ahead and start up. Great. So I'm not hearing any more questions, so I'm going to go ahead and close up. Thank you so much, Rahul. This was wonderful. And so everybody, if we have more webinars, we'll certainly let you know. Otherwise, we may be taking a break for the next bit, but we will definitely be starting up again. If you have any ideas on things that you'd like to learn about, please let us know. But otherwise, then we will start up again in August, September. Okay, thank you so much. And thank you again, Rahul.
Thank you very much. Have a nice time, everyone. Bye-bye.